Hi guys, I wanted to take a little time today and work with concept of the mole. This is something we covered before, but I think that it's worth taking another look at. And this is going to be very important when we switch ourselves over to our next subject. So, the mole itself is nothing more than a unit, and it's a convenience that comes from having to deal with very, very large numbers of individual molecules or individual atoms. So the number itself is famous, and it's Avogadro's number. It's 6 times 10 to the 23rd. And that number is named in the honor of a scientist who studied gases and discovered that no matter what the gas was, there's the same number of molecules present. So in order to help you think about a mole and what it is, you can think of it in a couple different ways. If you were able to count from 1 to Avogadro's number at the rate of 10 million a second, it would still take you 2 billion years to count the atoms in 1 mole. All right, so one way to remove some of the intimidation is to put Avogadro's number to side for a minute and look at the way we use units in everyday life. So if we have a unit called a wrap and it contains 8 objects, we would be able to answer the question, how many paper clips in one wrap? So if we were writing this as a conversion factor, we would write this as 1 wrap equals 8 objects. All right, so we can use this kind of logic to continue forward. How many oranges in 2 wraps? So we could get really formal and we could say 2 wraps and 8 oranges per wrap. The units cancel and you get 16 oranges. All right. So the mole, as we said, is just another number collector. It's another unit. All right, so we could have a dozen of something, a dozen cookies, and we can have a mole of cookies. Okay, so a mole of particles always contains 6 times 10 to the 23rd particles. Now, if we're talking about a pure substance, pure carbon, we can say a mole of carbon is 6 times 10 to the 23rd atoms. If we want to talk about molecules, we can say, my file got a little corrupted here, 6 times 10 to the 23rd molecules of water. If we have sodium chloride, we can talk about 6 times 10 to the 23rd formula units. Now the reason these are called formula units is that they're only ionically bonded, right? So they're not molecules. So we would say 6 times 10 to the 23rd formula units of sodium chloride. Okay. All right, so this, one way to look at Avogadro's number is just another conversion factor. So we have 6 times 10 to the 23rd particles per mole. I apologize, my file got all messed up here. Right, or 1 mole equals 6 times 10 to the 23rd particles. Right. And a particle can be an atom or a molecule. Right, so the way we use this is we can go back and forth between moles and numbers of atoms. All right, as a simple conversion factor. If we want to know the number of atoms in 0.5 moles of aluminum, we simply say we have 0.5 moles of aluminum. And then we know we want 1 mole to cancel because we want our units to cancel. And we have 6 times 10^23 atoms per mole. Okay, so our units would cancel, and we'd get 3 times 10 to the 23rd. I think that would be our answer. And you can go backwards too. This is a little bit corrupted again, but if you had 1.8 times 10 to the 24th atoms of tin or of sulfur, and you wanted to know how many moles you had, you could say 6 times 10 to the 23rd atoms gives me 1 mole. All right. Again, 10 to the 23rd would cancel. Atoms cancel. You still have 110 up here. So you'd get 18 over 6, which equals 3 moles. All right, a bit messy, but I think you follow me. Okay, so molar mass. Now, before we talked about atomic mass units, we talked about the weight of 1 atom of carbon dioxide, for example. Right? But now we can talk about the weight of 1 mole of carbon dioxide. Right? They happen to be the same number with different units. So if we, for example, have 1 mole of carbon atoms, it weighs 12 grams. If we have 1 carbon atom, it weighs 12 atomic mass units. Okay, so the number is the same. The unit is different. Okay, these numbers, might want to pause for a minute and get out a periodic table. These numbers come from periodic table. They are equal to the number of protons plus the number of neutrons. All right, these are not magical numbers I'm making up here. Okay, so we can do this for any atom. We can get the molar mass. So this number, the other way to express this is grams per mole. All right, now you'll notice I abbreviated mole a little bit. All right, so the molar mass of carbon is 12 grams per mole. Okay, so sometimes we use a couple different names. If you have a single molecule, the mass is measured in AMUs, as I said, but with the same numerical value. If you have a ionic compound, we usually talk about formula weight. Okay, The point is, you hear all the same terms, but they mean the same number just with different units. Okay, so let's put this stuff to use. Let's show you how we might use this. All right, I'm going to skip over this. Okay, for example, here's what I'd like to talk about. We want to know the molar mass of calcium chloride. All right, and the way we get that is just to sum up all of the components, and then we get the molar mass of the, in this case, it's a formula weight for the compound. Right? So, 1 mole of calcium, 40 grams per mole. 2 moles of chloride, chloride ions at 35.5 grams per mole gives you a total of 71. So 40.1 plus 71 equals 111.1 grams per mole. That is the molar mass of calcium chloride. Okay, so we'll go through some more examples here. Let's take this one here, aluminum hydroxide. This is in your Plop Plop Fizz Fizz antacid tablets. So how would we figure this out? What we do is this is a divide and conquer strategy where we take the, excuse me, I'm wrestling my periodic table. So aluminum has a mass of 27 grams per mole. Hydroxide, oxygen is 16 plus 1 for the proton. All right, so you have 51. Look at me, I'm on there. Right, okay. 51. So 51 grams per mole for your 3 hydroxides. You add those up, you get 78 grams per mole. Okay, so we could do this again for a more complicated molecule. This is Prozac. So C17, that would be 17 times 12 from the periodic table, 12 grams per mole. We have 18 times 1 gram per mole for our hydrogen. We have 19 times 3 for our fluorine. And then we have 1 times 16 for our oxygen. So this would be carbon, hydrogen, fluorine, oxygen, and for some reason I wanted to skip nitrogen. So 1 times 14 mole. Nitrogen. Okay, so you figure all those out, you add those up, and that gives you your total. Okay? Alright, so that's part 1. At some point we'll come back and take a look at this again.